Good afternoon, sir. Myself Monica. My topic is about Fourier transform from Fourier series Fourier transform of singularity function. Introduction to Fourier analysis. Engineering relevance. Fourier analysis forms the mathematical foundation for signal processing control systems and communication engineering. It enables engineers to analyze complex waveforms by decomposing them into simplified sinusoidal components. Signal classification. There are two types of signal classification: periodic signals, non-periodic signals. Periodic signals repeat over fixed intervals. Non-periodic signals do not exhibit repetitive patterns. Signal can be classified into several categories based on their characteristics and properties. Here are some main classification based on time. Continuous time signals defined for every instant of time. These signals have a continuous value. Example include analog audio and radio waves. Discrete time signals defined only at specific time intervals. These signals have distinct or discontinuous values. Example include digital audio and sampled data. Based on symmetry, there are two types of symmetries: even signals, odd signals. Even signals symmetrically about the vertical axis, meaning f of t equals to f of minus t. Examples include cosine waves. Odd signals is an asymmetrical about the origin, meaning f of t equal to minus f of minus t. Example include sine waves. Based on periodicability. Determinate signals complete periodicable with a fixed and regular pattern. Example include sinusoidal waves and polynomial functions. Random signals unpredictable with irregular patterns and uncertainty. Examples include thermal noise and financial market data. Based on energy and power. Energy signals have finite energy over an infinite period with zero average power. Example include aperiodic signals like decaying DC signals. Odd signals any symmetrical about the origin, meaning f of t equal to minus f of minus t. Examples include the waves. Based on periodicability. Determinate signals completely predictable with a fixed and regular pattern. Examples include sinusoidal waves and polynomial function. Random signals deterministic signals completely predictable with a fixed and regular patterns. Example include sinusoidal waves and polynomial function. Random signals based on energy and power. Energy signal having finite energy over a infinite period with zero average power. Example include aperiodic signals like decaying DC signals. Power signals have finite average power over any finite time interval but infinite energy overall. Example include periodic signals like sine wave and square waves. Based on periodicity, periodic signals repeat themselves after a fixed time period with characteristics waveform. Example include sine waves, square waves and triangular waves. Aperiodic signals do not repeat themselves at regular intervals with no characteristics waveform. Example include random signals and transist signals. The Fourier transform can be derived from the Fourier series by considering a periodic signal with an infinite period. Steps. Start with the Fourier series representation of a periodic signal. Express the Fourier's coefficient xn as the period t approaches infinity. Omega naught becomes infinitely small. Replace the summation with integration. Define the Fourier transform. The Fourier transform represents the frequency domain representation of the signal x of t, while the inverse Fourier transform reconstructs from x omega naught. The Fourier transform is an extension of the Fourier series to non-periodic signal, providing a powerful tool for analyzing signals in the frequency domain. To transition from Fourier series to Fourier form. Fourier series represent periodic signals as a sum of harmonically related sinusoids. Discrete frequency spectrum. Fourier forms. Extend Fourier series to non-periodic signals. Represent the periodic signal with the sum of harmonically related sinusoids. Discrete frequency spectrum. Fourier transform extends Fourier series to non-periodic signals, represent signals in the continuous frequency domain. It is defined as x omega integral minus infinity to infinity x of t e omega t dt. The differences of Fourier series, discrete spectrum, periodic signals, Fourier transform, continuous spectrum, non-periodic signals. Applications of Fourier transform. Fourier transform is widely used in signal processing, image analysis and communication systems. The Fourier series is the widely used in signal processing, image analysis. The Fourier transform provides a powerful tool for analyzing signals in the frequency domain and enabling the decomposition of complex signals in their consistent frequency. General notes: delta 1 frequency domain constant, step pi omega of plus 1 signum derivatives of powers of j omega. Conclusion and applications. Signal analysis. Fourier transform enable frequency domain analysis of signal, revealing spectrum, content and filtering characteristics essential for digital signal processing. Signal analysis. Fourier transform extends Fourier series to non-periodic signal, represents signals in the continuous frequency domain. Fourier series, discrete spectrum, periodic signals, Fourier transform, continuous spectrum, non-periodic signal. The applications of Fourier series of conclusion. Fourier transform is widely used in signal processing, image analysis and communication systems. The Fourier transform enable frequency domain analysis of signals, revealing spectral content and filtering characteristics essential for digital signal processing. Control system. System stability and performance analysis rely heavily on frequency. A Fourier transform extends Fourier series to non-periodic signals like represent signals in continuous frequency domain. It is defined as x omega equals to integral minus infinity to infinity x of t e j omega t dt. The differences of control system and signal systems are: Fourier in signal analysis, Fourier transform enable frequency domain analysis of signals, revealing spectral. Thank you, sir.